Despite its successes, the Bohr model suffers from a number of limitations. First, the Bohr model was only designed to work for one-electron systems, such as the hydrogen atom and the helium plus 1 and the lithium 2 plus ions. It does not work for multi-electron systems, such as the rest of the atoms in the periodic table. Second, the Bohr model of the atom places electrons in precisely defined orbits, as we see here in this diagram. The problem with this is that it disobeys the Heisenberg uncertainty principle, which tells us that we cannot completely define both the momentum and position of an object. So if we know something about one of those properties, then we cannot completely define the other property, such as its position. And so, therefore, the Bohr model of the atom is not a good description of the electrons in an atom. A better model is the quantum mechanical model of the atom. In the quantum mechanics, an electron is represented as a wave, and therefore the atomic orbitals are represented by a probability distribution maps, as we see here, where the higher density of the dots represents a higher probability of finding an electron in that position. This is a statistical picture of where the electron is most likely to be found. And so the electron therefore becomes a probability wave. And this is the most accurate model that we have of an atom.
Schrödinger introduced the concept of the wave function, which we represent by the Greek symbol psi. And this is a mathematical description of the wave-like behavior of the electron in three-dimensional space. This three-dimensional representation is what we call an atomic orbital and should not be confused with the two-dimensional orbits that we studied in the Bohr model of the atom. These wave functions can be characterized by three specific parameters, n, l, and m, which we call quantum numbers. And we'll learn a little bit more about each of these quantum numbers in the following slides. The first quantum number we will look at in the wave equation is n, also known as the principal quantum number. N must be a whole number, and allowed values for n range from 1, 2, 3, 4, and so on. The principal quantum number describes the distance of the orbital from the nucleus. Below we have figures for three orbitals for n equals 1, n equals 2, and n equals 3. These correspond to the 1s, 2s, and 3s atomic orbitals. As you can see, as n, the principal quantum number, increases, the orbitals get larger, and therefore the electrons become farther from the nucleus. The second quantum number is the angular momentum quantum number, which is represented by the symbol L. Allowed values for L depend on n, and they must be positive integers starting at 0 and going all the way up to n minus 1. So for example, if n equals 1, then L can only be 0. However, if n equals 2, then L can be 0 or 1. And if n equals 3, then L can be 0, 1, or 2. The significance of the angular momentum quantum number is that it describes the shape of the orbital. So for example, L equals 0 is completely spherical, which we call an s orbital. L equals 1 is dumbbell shaped and is given the name p orbital. L equals 2 has 4 lobes, and we call this a d orbital. And L equals 3 is an f orbital. So just to recap, the angular momentum quantum number L describes the shape of the orbital or the type of the orbital. Now you might be wondering where the labels S, P, D, and F came from. Well, the historical reason for those names is that when physicists were looking at the emission spectra that arose from those orbitals, they noticed that some of the orbitals were sharp, which is the name for the s orbital. Some of those emission lines were principal lines, and that's a name they gave to the p orbitals. Some of those lines were diffuse, which is a name they gave to the d orbitals, and then some of the lines were fundamental lines, which is a name given to the f orbitals. The third quantum number is the magnetic quantum number, which is given the symbol m sub l, or ml. Allowed values for ml depend on the value of L, and they must be integers ranging from negative L going through to 0 and then all the way to plus L. So for example, when L equals 0, which is an s orbital, then ml can only equal 0. However, if L equals 1, which is a p orbital, then ml can be negative 1, 0, or plus 1. And finally, if L equals 2, which is a d orbital, then ml can equal negative 2, negative 1, 0, plus 1, and plus 2. The significance of the magnetic quantum number, ml, is that it describes the orientation of the orbital in space. Let's take a look at the magnetic quantum numbers in more detail. We'll start with L equals 0, which is the case for the s orbital. Here's a picture of an s orbital here, and we can see that it is completely spherical. In this case, the orientation doesn't really matter, so there can only be one s orbital. Looking at the magnetic quantum number, when L equals 0, there's only one possible value for ml, and that's ml equals 0. Again suggesting that there can only be one s orbital. Now let's take a look at the case of the magnetic quantum number for when L equals 0, in other words, the p orbitals. When L equals 1, then the magnetic quantum number, ml, can have three possibilities. ml can equal negative 1, 0, or plus 1. This corresponds to the three different p orbitals, px, pz, and py, respectively. And here we can see the three different orientations for the three p orbitals. Now it's important to remember the characteristics of the p orbitals and how they differ from the s orbitals. You can see here that each of the p orbitals has a nodal plane. And we can see that in each one of the p orbitals. The nodal plane is a special region where the electron density for the orbital equals 0. Another important feature of the p orbitals is that the lobes for each of the p orbitals have different phases. So as we go from the left side through the nodal plane to the right side, we can see that the phase of the wave changes from blue to red, and vice versa. And this feature is present for each one of the three different p orbitals. At the bottom here, we've put each of the three p orbitals together. Still looking at the p orbitals, you might be asking yourself what the phase of the wave is supposed to represent. Here we've colored them blue and red. Well, on the diagram at the top here, I've drawn a sine wave, as you might remember it from high school. You can see that for a sine wave, part of the wave lies above the x-axis and part of the wave lies below the x-axis. If we color the part of the wave above the x-axis in blue and the part of the wave that is below the x-axis in red, these would represent the two different phases, just like we see for the p orbital. Now these p orbitals are drawn in 3 dimensions. However, for your midterms and final exams, when you're asked to draw the orbitals, you would be expected to draw them only in 2 dimensions. And the diagrams shown below here represent how you would be expected to draw the p orbitals on your midterm or final exam. Here we look at the magnetic quantum number, ml, for the case where L equals 2, in other words, the d orbitals. Now, if you remember, ml must be an integer starting at negative L, going to 0, and then going all the way to plus L. And so because L equals 2, the allowed values for ml are negative 2, negative 1, 0, plus 1, and plus 2, respectively. And these correspond to the 5 d orbitals, dx squared minus y squared, dxz, dz squared, dyz, and dxy. We can see here that the d orbitals each have 2 nodal planes, which are shown right here. At the bottom here, we've plotted all 5 of the d orbitals together to show you what they could look like. Again, on both the midterms and the final exams, you will be expected to be able to draw the d orbitals in 2 dimensions. And at the bottom here, we've shown you how they should be drawn in 2 dimensions. We can see here that the nodal planes, where each d orbital has 2 nodal planes, for 3 of the d orbitals, those nodal planes lie along the axes. For one of the d orbitals, the nodal planes lie between the axes, and that's the case for dx squared minus y squared. Dz squared is a little bit different because it doesn't have 2 nodal planes, but it has 2 nodal surfaces or nodal cones shown here. So once again, you should be able to draw the d orbitals as well as draw the nodal surfaces or nodal planes. Here we look at the magnetic quantum numbers, or ML, for the case where L equals 3, or the f orbitals. Once again, because ML must be an integer that starts at negative L, goes to 0, and then goes all the way to plus L, the allowed values for ML are negative 3, negative 2, negative 1, 0, plus 1, plus 2, and plus 3. So we can see that there are 7 f orbitals. Now, you might notice that the f orbitals are somewhat complicated. So the good news for you is that you are not responsible for drawing f orbitals on the midterm or the final exam. However, you should be familiar with them and what they look like. As you may recall, the wave function psi is characterized by 3 quantum numbers: the principal quantum number, n, the angular momentum quantum number, L, and the magnetic quantum number, ML. Now, it's important to remember that that wave function was derived for a 1-electron system, for example, hydrogen. However, you might notice that all the other elements in the periodic table, other than hydrogen, have more than 1 electron. So in order to account for multi-electron systems, we have to introduce another quantum number, which is the spin quantum number, ms. Now, I just want to take a step back for a minute so that we can explain how the spin quantum number was deduced. And it happened through this type of experiment. A source here generates a beam of atoms. And if those atoms have an odd number of electrons, in this case silver atoms, then, and that beam of atoms is passed through a magnetic field, then something very surprising happens. Because you would expect those atoms, which are all identical, to be deflected by the magnet in all the same direction. However, what actually happens is half the atoms are deflected down and the other half of the atoms are deflected up. So what could be causing this? Well, as we know, electrons are charged particles. And the analogy that we're going to use is that those electrons which are charged are spinning. Some of them are spinning clockwise, and some of them are spinning counterclockwise. Okay. And because those electrons are charged, when they spin, they create a magnetic field. Okay. And because they're spinning in opposite directions, the direction of that magnetic field will be the opposite if they're spinning clockwise than if they were spinning counterclockwise. So this leads us to the spin quantum number, right? Allowed values for ms, the spin quantum number, are +0.5 and -0.5. Symbolically, we often represent that as spin up with an up arrow and spin down with a down arrow for the spin -0.5. Okay? And this leads us to a very important concept, which is the Pauli exclusion principle, which states that no 2 electrons in an atom can have the same 4 quantum numbers. And by quantum numbers here, we mean n, l, ml, and ms. So no 2 electrons in an atom can have the same values for n, l, ml, and ms. What that means is that if they have the same values of n, l, and ml, then they have to have different values of ms. One electron has to be spin up, the other electron has to be spin down. In other words, each atomic orbital can hold a maximum of 2 electrons. If one electron is spin up, or spin plus a half, the other electron must be spin down, or spin minus a half.
In addition to the principal quantum number, n, the angular momentum quantum number, L, and the magnetic quantum number, ML, we also introduced the spin quantum number, MS, which has allowed values of plus a half and minus a half. So, for the example where n equals 3, and remember that the principal quantum number n can have allowed values of whole numbers starting with 1 going all the way to infinity. The angular momentum quantum number L can have allowed values of 0 going all the way to n minus 1. So in this case, when n equals 3, L can have allowed values of 0, 1, and 2, where L equals 0 would represent an s orbital, L equals 1 would represent a p orbital, or the p orbitals, and L equals 2 would represent the d orbitals. So here we have a 3s, 3p, and 3d orbitals. Now, when L equals 0, ML, which can have allowed values ranging from minus L going to 0 and then all the way to plus L, when L equals 0, ML can only have a value of 0. And so this would represent a 3s atomic orbital, and in each orbital we can place a maximum of 2 electrons. The first electron would have a spin quantum number of plus a half, and then the second electron would have a spin quantum number of minus a half. In the case of our 3p orbitals, where L equals 1, ML can have allowed values of minus 1, 0, and plus 1, which would represent the 3px, 3py, and 3pz atomic orbitals. And in each of these 3p atomic orbitals, again, we can have a maximum of 2 electrons with spin plus a half and minus a half. The first electron always has a spin of plus a half, and the second electron in an orbital always has a spin of minus a half. And so in each of these 3p orbitals, we can have 2 electrons each, and therefore we can have a total of 6 electrons in our 3p atomic orbitals. Now, when L equals 2, the allowed values for ML are minus 2, minus 1, 0, plus 1, and plus 2. And these values of ML represent our 5 3D atomic orbitals. And again, since each atomic orbital can have a maximum of 2 electrons, where the first electron has a spin of plus a half and the second electron has a spin of minus a half, we can have a total of 10 electrons in our 5 3D atomic orbitals.
Here I would like to summarize the concepts we have learned about quantum numbers for the case when n, the principal quantum number, equals 1, 2, or 3. When n equals 1, the angular momentum quantum number, with L, which must be a positive integer starting at 0 and going to n minus 1, must be 0. Also, the magnetic quantum number, ML, which must be an integer starting at negative L, going to 0, and then going all the way to plus L, only has one option, and that's ML equals 0. So we can see when n equals 1, we only have a 1s atomic orbital. When n equals 2, then the angular momentum quantum number L can be either 0 or plus 1. When L equals 0, then ML can only be 0, and this would be the case for the 2s atomic orbital. However, when L equals 1, then ML can be negative 1, 0, or plus 1, which corresponds to the 2px, 2py, and 2pz atomic orbitals. When n equals 3, then the angular momentum quantum number L can be 0, 1, or plus 2. When L equals 0, ML must be 0, and this would correspond to the case of the 3s atomic orbital. When L equals 1, then ML must be negative 1, 0, or plus 1, which would correspond to the case of the 3px, 3pz, and 3py atomic orbitals. When L equals 2, then ML must be negative 2, negative 1, 0, plus 1, or plus 2, which corresponds to the case of the 3D x squared minus y squared, 3D xz, 3D z squared, 3D yz, and 3D xy atomic orbitals, respectively. So you can see that for the case where n equals 1, there's only one orbital that can have the value of n equals 1, and this is the 1s atomic orbital. However, when n equals 2, then we can have 2s and 2p atomic orbitals, giving us 4 possible atomic orbitals for n equals 2. Finally, for the case when n equals 3, then we can have 3s, 3p, and 3d atomic orbitals, giving us 9 atomic orbitals for the case where n equals 3. In this example, we are asked to indicate the possible sets of quantum numbers for a 3p atomic orbital. Once again, the strategy is to use the selection rules for each one of the quantum numbers. For the principal quantum number n, it must be a whole number starting at 1. For L, the angular momentum quantum number, L must be a positive integer starting at 0 and going all the way to n minus 1. And for the magnetic quantum number, ML, it must be an integer starting at negative L, going to 0, and then going all the way to plus L. So, the 3p atomic orbital. 3 indicates the principal quantum number, n equals 3. P indicates L equals 1. So, therefore, allowed values for ML would be negative 1, 0, and plus 1. Where n equals 3, L equals 1, and ML equals negative 1 would correspond to the 3px atomic orbital. N equals 3, L equals 1, ML equals 0 would correspond to the 3pz atomic orbital. And n equals 3, L equals 1, and ML equals plus 1 would correspond to the 3py atomic orbital.